Hello everybody. My name is Morten Dahlen. I am at dScience, and I will say a couple of words about dScience first before I'm going to introduce today's speaker. dScience is a center organizing activities across departments, across faculties, to communicate science out to public between ourselves. We are basically doing these things, and we have a series of events like this. This is almost full today as well, and this has been a very popular event. We have events for PhD candidates in our lounge, and we also have the big Data Science Day every year. That's going to happen on the 17th of October this year. This is one of this spring's lectures here at the Science Library, and I have to say we are doing this together with the Science Library. And today we have Trude Storelvmo. Trude Storelvmo, she is professor at the Department of Geosciences within the Metos group. She has a long CV that I don't remember. But and she is going to talk about a topic that I'm really looking forward to hear about. It's about climate and the combination of and the relation to economy. And the floor is yours, Trude. Looking forward to this. Oh. Give her a big hand.
Oh, thank you. Thank you. Thank you very much, Morten, and thank you all for coming here. It's great to see that so many are interested in our research and the interface between climate change and the economy. I have to say this is a project that has been extremely interesting, one of the most fun and also challenging projects that I've been involved in so far in my career, and actually started about a decade ago now when I was working at Yale University, and I found myself surrounded by a lot of really brilliant economists that were also really generous with their time and interested in working across disciplines and interested in the problem of climate change. And we're working with one of those economists, even today, Tony Smith, who is still at Yale. So this is a collaboration between Yale University, University of Oslo, and Nord University here in Norway. So I should say, in recent years, this project has been moved forward first and foremost by the person who is highlighted here on the screen, Jenny Bjordal, who's also in the audience. She's currently partially on maternity leave while finishing her PhD thesis, so therefore I'm on the stage today, but I encourage you all to come to her PhD defense after the summer, and I really want to make sure I give full credit to her work. So yeah, this work deals with global simulations of the interactions between climate change and the economy. And it was originally funded by a Yale seed grant for interdisciplinary work, and more recently has been funded by the Directorate of Higher Education and the Norwegian Research Council. So I'll go right ahead, and I'm sure this audience doesn't need much of background when it comes to the problem of global warming. So I thought I would just show this for backdrop, which is the iconic warming stripes that, in a sort of artistic way, illustrates how the global mean temperature, starting from pre-industrial times on the left and ending with 2023 on the right, shows how our global mean temperature has been steadily increasing, and 2023 turned out to be the warmest year on record at about 1.5 degrees above pre-industrial times. And so if you're wondering if that means that we've already breached a 1.5 degree limit, that's not quite the case, because we consider that to be true only when we have exceeded 1.5 degrees over a longer period of time, but we're certainly getting there. And so I'm sure you all have a good understanding of what has been driving this global warming, but to sort of give you a quick schematic of it, I've borrowed this chart here, And I've actually been so bold as to take it from the Nobel Prize lecture of William Nordhaus, who was another economist that I was able to interact with at Yale University. And he got the Nobel Prize in economics in 2018 for his work at the interface between economics and climate change. And so he called this chart the circular flow of global warming, science, impacts, and policy. And to go through it quickly, it starts on the upper left box with economic growth, which leads to CO2 emissions through all the activities that we undertake in our daily life. And with those rising CO2 concentrations, along with a few other climate forcers, that leads to climate change, which materializes through higher temperatures, but also precipitation changes, changes in extreme sea level rise, and so on. That in turn has an impact on the ecology and also has economic impacts. And so far, the link between these boxes is clear and robust. But then where there are question marks is to what extent these climate change impacts on the economy in turn lead to changes in climate policies, and whether that then in turn has an influence on our emissions or the link between economic growth and emissions. And so this is probably a good time to say I have no training in economics whatsoever. So full disclosure, the closest I get is that I'm married to an economist. So I should say this, but my understanding and the way economists speak about this is that they call these impacts, these unintended impacts of economic growth that we see, whether it's ecological impacts or economic impacts, they call them an externality, something that is either unpriced or underpriced in the current market. And that is essentially the crux of the problem or the inconvenient truth of this flow chart. And so this flow chart also serves as the structure for what we call integrated assessment modeling. So when you model economic impacts of climate change, it sort of follows this general flow chart. And this actually takes me back to one of the first talks that I attended where I saw Nordhaus and other economists at Yale presenting their work. And I saw a figure looking something like this. And it is based on Nordhaus's pioneering modeling work. He created one of the first integrated assessment models, which he called the DICE model, but at the time, this was a model that only dealt with global average quantities, whether it was the economy or the climate. But when I attended this talk, they had developed this model quite a bit further, and so they were now able to simulate geographical distributions of economic consequences of climate change. And so at this point, the model had a new name, DIAM, which is short for Disaggregated Integrated Assessment Model. It's a bit of a mouthful, but it's simply the original globally aggregated Nordhaus model that had now been turned into a gridded model. So it had a grid of 1 by 1 degree longitude, latitude, and so could simulate the geographically heterogeneous impacts of climate change. And so what I'm showing you here, which is more or less what I saw at the time, is change in GDP in 2100 for what I've called here a business as usual scenario. It's a no policy scenario, if you like. So a simulation where there is an optimization when it comes to economic growth without any climate policy imposed. And what blew my mind at the time was that in this simulation, global mean temperatures had risen by something like 3 to 4 degrees in 2100, which for a climate scientist is a really strong global warming and something that we think of as potentially catastrophic in a number of ways. But when I looked at this map, I actually saw a large regions of the world seem to benefit economically from this much global warming. And certainly you see negative values in blue shades there in the global south, but certainly in our part of the world and much of the developed world appear to be benefiting from what, in my opinion, as a climate scientist, was a very strong and potentially dangerous amount of global warming. And so that got me really curious and interested. And another thing that struck me was that, this model is starting to look a lot like a climate model. Because our models too, as you'll see in a little bit, are also gridded with a similar kind of grid spacing of about 1 by 1 degrees. And so I started to wonder, is there a potential here to get two models from these two different fields and modeling worlds to communicate? And so that sort of started the work that I'll be presenting now. What I quickly realized was that a basis for the map that I just showed you was what is known as the damage function. And here's an example of a damage function, and it happens to be Nordhaus's damage function. It just shows as percent of global GDP how much that is expected to be reduced for a given global mean temperature increase. And you also see here some, so the green curve is the Nordhaus curve, and you also see a few other symbols. You see estimates from an IPCC report, and so you should immediately take away from this that there's quite a bit of uncertainty surrounding the damage function and what exactly it should look like. And so that's something that you should absolutely take away from this talk, and something that I'll come back to. So when Nordhaus got the Nobel Prize, it wasn't so much for coming up with a perfect damage function, but it was for pioneering this field of research, for opening up this as an important area of study in economics. And so indeed, he got the Nobel Prize with the motivation that he had been integrating climate change into long-run macroeconomic analysis. And indeed, it has grown tremendously as a subfield of economics in recent years. I also want to sort of advertise that Bill Nordhaus wrote more like a popular science book a few years ago called The Climate Casino that I really enjoyed. It sort of helped me in understanding some of the very complex aspects of the economics of the problem, so it might be something that you're interested in checking out yourself. But the reason I'm mentioning it here is that we have been borrowing the term climate casino for an application that I'll show you towards the end of the talk. So you'll see that appear also later in the presentation. So like I said, this globally aggregated model that Bill Nordhaus had developed now almost half a century ago had been turned into this model that we now call DIAM. And when you do that, you're simulating economic damages with geographic heterogeneity. And if you at the same time require that these regional damages must average up to the original Nordhaus function, which is what was done in this model, something like this comes out. And so it essentially says there is a temperature where optimum productivity occurs. And if you're colder than that optimal temperature or warmer than that optimal temperature, you'll have lower economic productivity than you have at the maximum. And so you might be asking yourself, well, how confident are you that this function should look exactly like this, that it should be peaking at 11 degrees and have this exact shape? Not confident at all. So this I'll come back to. But the general feature, I think, is something that we have an intuitive feeling for. We have a feeling for the fact that if it gets excessively warm, that's not ideal for economic productivity. If it gets extremely cold, that's also not optimal for economic productivity. So the general form of the function, I think we have an intuitive feeling for it being right. But whether it should look exactly like this, I think I'll demonstrate later on that that's a very open and active field of research. So yeah, I said this DIAM model has a resolution of 1 by 1 degree. It has a time step of 1 year. So it integrates forward in time 1 year, 1 by 1 year, 1 by 1 year. So this is very different from what we do in climate modeling. So our time step is much, much shorter. So this was one of the things that became clear, that there's a scale mismatch between these two modeling tools. This model, while it can be viewed as sort of state of the art, it still makes a lot of assumptions. And at the moment, the only damage from climate change occurs through temperature. And again, I'm sure you all have an intuition for other variables than temperature being important for economic activity, whether it is precipitation, whether it's sea level rise or extremes or whatever. So this is a clear limitation of this tool at the moment. This should say GDP, not BNP. There's the damage is on the GDP level, not on its growth rate. So this is also something that is debated among economists, whether it's the growth rate that should be influenced or the level itself. But in this model, it's the level itself. There's an underlying assumption that through technological advance, there will inevitably be a transition from fossil fuels to renewables over time. And there are also assumptions that capital can flow freely between regions and countries, but there's an assumption about no migration. And here, I'm sure you would all say this is clearly not realistic. And so this is the sort of the baseline model, and some things can be modified quite easily, and other things would require a lot more work to modify. But this is sort of the baseline model that we're starting with. Now, coming back to what this model gives us today, which is this extremely heterogeneous effect of climate change on the economy, where we saw that there are winners in the developed world and losers generally in the global south. And I just wanted to make the point here that that's not completely far-fetched. So this is a very overwhelming graph potentially from the last IPCC report, but it shows you in each row a different region of the world, and columns show you different sectors, whether it's agriculture or whether it's infrastructure, what have you. But what you can see here is that the different colors here represent the level of confidence we have on whether these regions and sectors would be affected positively or negatively by warming. And you do see that there are mostly minuses here, right? Certainly for many of the countries in the global south regions would have mostly minuses, meaning there are negative consequences to all sectors in this region. But there are also some pluses, right? Where it's possible that at least in the near term, there could be benefits in some sectors in some parts of the world. So this is not completely far-fetched. But whether it should be looking like the map I showed you is not clear at all. So you can see, for example, that Europe is an example of a region where some sectors could potentially benefit from warming. So I just want to be clear and open about this, that this is not necessarily controversial in itself. Now, coming back to this modeling activity, the idea of coupling this economic model with a state-of-the-art climate model, I want to now briefly talk about what we think of as a state-of-the-art climate model, or sometimes we call them Earth system models, simply because of all the different components and elements of the Earth system that they include. So here's the flagship Earth system model in Norway, NORESM, a model that we use, develop, love. And so this model too can be run at different resolutions, but a quite standard resolution is 1 by 1 degree, as we saw with the economic model. Now, the economic model has a 2-dimensional grid. The Earth system model has a 3-dimensional grid, because what it does is that it solves equations that govern fluid flow and thermodynamics in the ocean and the atmosphere. And it has components representing the atmosphere, ocean, sea ice, ice sheets, land components, vegetation components, and so forth. So pretty much anything you can imagine in the climate and the Earth system, there are attempts to represent it in these models. Not all of it can be represented by fundamental equations, but then these processes are what we call parameterized to represent their effects on things like the temperature or precipitation and so forth. So as you can imagine, this is a computationally very heavy model to run. I think I wrote on the previous slide here that this economic model, in comparison, is computationally very lean. It's a very cheap, would be a very cheap additional component to the NORI-SM model, simply because of the vast number of processes and the vast number of grid boxes in which you integrate equations forward in time. So these models have similarities and they have differences. And the differences, of course, have turned out to be a bit of a challenge as we moved forward to try to get these models to talk to each other. And in case you're scratching your head over why we want to do this now, and you don't quite see why we would go to all this effort, I'll try to explain this here in terms of the limitations that each modeling tool has on its own, and that some of these limitations could be overcome if we couple the two. So on its own, DIAM, the economic model, has an extremely simple representation of the climate system. In fact, I think it's 2 equations. So it calculates a single climate variable, global mean temperature, and then it has a function that kind of gives the geographical distribution of that temperature. So it cannot capture other climate variables than temperature. It cannot capture climate variability. It cannot capture extremes. And so we argue that this is going to limit this model's ability to realistically simulate all aspects of climate change and to represent the geographical distribution of the damages from that climate change well. So, and on this slide, I also sort of try to illustrate some of the extreme events that we are well aware have had tremendous cost and had tremendous influence on the economy. So it becomes clear that it's not necessarily the temperature itself, but things that come along with temperature in a spatially heterogeneous way that influence the economy. But NORI-SM is also, as much as we're proud of our own climate model, it has a limitation in that it cannot simulate dynamically interactions between climate change and economic development. So what is done at present is that there are emission scenarios developed that are consistent with certain socioeconomic and technological development. But these are sort of delivered to the Earth system model, to NORI-SM, and a wide range of other Earth system models that use them, and they're static. There's no way that these policymakers can respond to how the climate evolves in a given model and then have an influence on the emissions. The emissions are static throughout the full length of the simulation, which can last for multi-centuries. And it just seems like an unrealistic way to represent the interaction between economic development and the climate system. Because, as you'll see shortly, there are a wide range of climate models, and the same emission scenario can give you a very different climate evolution in one climate model versus another. And so the question is then, should the emission scenario be static, or should it be should it be kind of a dynamic interaction there between the emissions and the climate evolution that it triggers? And we argue there should be a dynamic interaction. So we are quite convinced that this is a promising way forward. And so what we do is that we force these two models to talk to each other. And it seemed trivial at the time when I had this idea that, oh, these models have the same grid, let's just couple them together and simulate these interactions. But of course, there are a tremendous number of challenges, as Jenny can probably talk to you at length about. But the goal, and we're essentially there now, is that instead of these two simple equations that represented the entire climate system in the DIAM model, we now have NORISM simulating climate. At the moment, we haven't gotten further than the point where NORISM passes temperature evolution to the economic model. But nevertheless, there's still climate variability. There can be extremes, and so there's still a lot more. The temperature field is already a lot more dynamic than it would have been in the economic model itself. So these temperature fields are passed on to DIAM once a year. So DIAM only exchanges information with NORISM once a year, whereas NORISM has a time step of half an hour, DIAM has a time step of 1 year. So once a year, they talk to each other. One passes temperature on to the other. Then DIAM does its calculation, where the end goal is to really generate a future path of optimal economic activity to enhance welfare. But of course, that then generates emissions, which is what is passed on back to NORISM, and then NORISM uses those emissions that come from DIAM to simulate the climate evolution onward in time. And of course, in DIAM, there's the damage function that then is the way that temperature can influence economic activity and sort of damage activity and reduce productivity or reduce GDP. There's also an option in DIAM to impose a carbon tax. And so that sort of increases the cost of production, so that that has the effect of limiting productivity and therefore also limiting emissions, which is the general goal of imposing a carbon tax in the first place. And so this is a very simple schematic of how the model works today. Yeah, so then we've generated a global model which has these dynamic interactions between climate and the economy with a high degree of geographic resolution. So that's still 1 by 1 degree. And now we're at the stage where this model can be used as a laboratory to simulate distributional effects of climate change on the economy and to explore different climate policies. So we're at a very exciting stage with this research where we're now ready to apply it for the purpose of a lot of research questions and also for educational purposes, as I'll talk to you about shortly. And because of the richness of the climate variables that are simulated by NORISM, which is pretty much any variable, climate-related variable that you can imagine, we now have the ability to calculate damages due to other things than just temperature change. And thankfully, there are now damage functions becoming available that are not just functions of temperature, but functions of other climate variables as well. For example, precipitation. So I'm showing you here, these are essentially on top just decadal trends in temperature for different regions based on observational data sets, and the same thing for precipitation below. I don't remember now exactly what time period, but in recent decades. And what you see right away is that while there's global warming, there's warming everywhere. in recent decades, to various degrees, but there's widespread warming, and the sign of the change is the same everywhere. That's far from being true when it comes to precipitation changes. So with global warming, and this is well understood from a sort of climate physics point of view, why this is the case, but you see, you see here that the precipitation changes are extremely heterogeneous in space. So you have regions with strong reductions in precipitation with warming, and also regions with strong increases in precipitation with warming. Our region is a region with strong increases in precipitation. And so immediately you see that this adds a lot of spatial heterogeneity to the impact of precipitation. And so coming to this damage, these new damage functions that account for more than temperature. Here's a brand new study where the lower left plot here shows a traditional damage function that is a function of temperature only. So I should say the y-axis here now is essentially just reflecting, is a metric of damage. Yeah, it represents the damage function. So you see the optimal temperature showing up here as it did in the curve earlier on the lower left-hand side. But the two plots on the top here show that in this new analysis, where they also look at effects of precipitation, so what is called PRE here, you see that now there's actually also sensitivity to precipitation. There's a stronger sensitivity to temperature, but there is also a sensitivity in the economies. The study finds that the economy is also sensitive to precipitation. So it's now a curved surface. And the difference between the two top plots is that in one plot, interactions between temperature and precipitation are also taken into account, whereas on the top left, they're viewed as independent factors. And so you see a more curved surface if you take into account the interactive effects of precipitation and temperature. And this too is quite intuitive, right? Because you know that if you have extremely high temperatures and at the same time a drought, that is a lot more impactful than having high temperatures but no water limitation. And so the fact that there is an additional effect from the interactive effects of the two on economic factors is not surprising. So this is brand new work, but it's an example of the damage functions that are now becoming available that we can now use because we have information about climate variables beyond temperature. So that's exciting for us and something that we will eventually be able to build into our modeling framework. So before I talk to you about what I think is a really cool application, I'm running out of time, really cool application of this modeling tool, I wanted to quickly say we struggle with two big unknowns when we work on the interface between climate and economics. So one is what we call the climate sensitivity. So that's just how much warming you get for a given increase in greenhouse gases. And specifically, it gives you the warming for a doubling of CO2 in the atmosphere. And so here I'm showing you what the climate sensitivity is in the latest generation of climate models, and I've highlighted NORISM here, which is currently our model of choice. And so you see that NORISM is actually a model that has a relatively low climate sensitivity. You also see that there's an incredibly wide range of climate sensitivities simulated with state-of-the-art climate models. And this is sort of an Achilles heel or a bit of a headache in the climate modeling community. We really want to limit the range of plausible values for climate sensitivity. But this is something that we've struggled with for decades, and we are currently not really able to rule out any of these as implausible. But I just wanted to say, when we choose NORISM, we also choose implicitly choose to assume that climate sensitivity is relatively low, that we don't get that much warming per increase in greenhouse gas emissions. So that's something to acknowledge. And then the other big unknown comes from the economic side, and so it's not really our problem as climate scientists to solve, but it's the economists that need to work hard on this problem, and that's the damage function that I already talked about. And so we see now the graph has been reversed, so we now see the Nordhaus damage function, which shows reduction in productivity per degree of global warming in blue, and then an alternative damage function in orange that gives you a lot more damage per degree of warming. And there are more damage functions on the market as well, but these are examples of two damage functions that give you very different damages for the same amount of warming. And again, if you then turn this into something that can be used in this regional modeling context, where again you just require that the regional damages average up to these curves in the global average sense, you get the curves on the right here, and you see that qualitatively they look similarly, but they have slightly different peaks. Some level off more sharply, especially towards warmer temperatures than others. So again, here's another huge source of uncertainty. So the purpose of developing the model that we've developed that uses a climate model with a certain climate sensitivity and it also uses a certain damage function is not to tell you, here's the answer. Here's how the climate will evolve going forward. It's first and foremost a tool to explore important questions in the interface between climate and economy, but we do have to acknowledge these two major uncertainties, one coming from climate science and the other from economics. Jenny led a really nice study where she explored the impacts of using these different damage functions, and she also looked at two different climate models, so the NORISM climate model that has a low climate sensitivity, and also another climate model with a high climate sensitivity. And here we hadn't gotten to the point where we could sort of create our own climate scenario or emission scenario. So these are the standard emission scenarios that were used for the last IPCC report. So without going into great detail, the upper left is a low emission scenario, and then emissions increase as you move to the right and to the bottom here. So on the lower right, you have a very, very high emission scenario. But I'd like you to compare here, so these are global productivity changes. So I'd like you to compare the pale green curve and the sharp orange curve here. And so the pale green is a low sensitivity, low damage function world, and the sharp orange one is a high climate sensitivity, high damage world. And again, you see a very big difference here for the same emission path, depending on which climate sensitivity you believe is right and which damage function you believe is right. So this is something this is where the field is. We can't be more confident than this because of uncertainties coming from both fields. And I can't go into this in great detail, but if you think that the differences are large in the effects of productivity in the global average, here there are illustrations of different regions, different countries, sorry. The size of them are illustrated by the size of the symbol. And if you focus on some of them, you can see that depending on whether you are in the low or high or some other combination of the climate sensitivity and damage function combinations, you can have situations where one country will in one case benefit from a given scenario, and in another region there can be detrimental effects to the economy for a given scenario. So that's just, the differences are even larger if you go to the country scale or regional scale. Okay, now I've chosen to talk about a really cool educational application of the new modeling tool. So if you want to learn more about the research frontier of the new modeling tool, you have to go to Jenny's PhD defense or one of her talks or read her papers. But I wanted to showcase something that I think is really interesting, and that is a game that we call the Climate Casino game, so named after Nordhaus's book. And we've used this in several courses now, courses both for students in climate science, but also students, MBA students essentially, students in business and administration, and as a learning tool. And so I'll spend now my last few minutes showing you what we've done. So we divide the group of students into 5 groups that represent the regions that are highlighted here. So Russia, EU, United States, we've lumped China, Japan together, and then India. And the numbers here are the emissions that each country contribute with globally. It's a little bit outdated, but that's not so important. And then we ask each group to make decisions about carbon tax. And they have an individual goal as a group. They want to kind of achieve the best possible economic development, best possible welfare for the country or region that they represent, but they also have a common goal, which is to limit global warming to 1.5, or a secondary goal, 2 degrees. So should sound like a familiar goal to you. This carbon tax, we asked them to just simply scale what we call the standard carbon tax in the model. And if you are, for reference, you can follow the line on this plot for a tax of 1, and that shows you how the standard tax alone influences the economic productivity. And so what we ask the students to do is simply to scale their tax relative to the standard tax. And the tax becomes more aggressive with time, which is why the plot looks the way it does, right? So that is true for the standard tax, and therefore also when you scale it, that's true. Of course, in addition to the tax itself, which limits economic productivity, temperature will be influenced by your taxation, and that also can have either a detrimental or positive effect on your economy. So this is what we're asking them to do. Just give us a scaling factor. And we also tell them this. If you have a simulation with no tax, the emissions, global emissions in gigatons of carbon is the blue curve. And the corresponding global temperature evolution is the blue curve here on the right. And right away, you see that the climate system is, in fact, very messy and has a lot of variability, which is why the curve is so noisy. But you also have the horizontal lines here to guide your eye. And so you see in a no-tax simulation with this modeling tool, you fail to achieve both the more ambitious and the less ambitious temperature goal. You end up with a temperature at the end of century above 2. So the student groups know this. And we also show them the purple curve where emissions go down because there's a carbon tax imposed, in this case the standard carbon tax, and in this case you almost reach the global temperature target of 1.5 degrees. So this is what the students have to work with. And we first used our fellow climate scientists as guinea pigs. So there were about 30 of them that were willing to do this with us. And we told them you cannot talk to each other. So there was a game theory element in this as well, because they were supposed to tell us their carbon tax decisions without talking to each other or collaborating. And so they didn't know what the other groups decided to do. So each group made carbon tax decisions at the beginning of the time period, so in year 2020, and then we let them update their carbon tax decisions every 20 years thereafter. Long story short, because I'm running out of time, we see the emissions with no tax again in blue and with standard tax in purple. And we see that while there was some tax imposed by some of the regions, they were not imposed by all regions, and so there were some free riders in this case, and so and also some somewhat erratic behavior here by our fellow climate scientists, which in the end resulted in them failing to meet the target, the global temperature goal. And it served as a really interesting illustration of how this notion of fairness and equity, interregional equity, played a really important role. And we certainly saw the manifestation of frustration when people realized that some regions weren't really pulling their weight and not contributing free riding while they were letting others solve or deal with the common problem of global warming. So, but I should say to the defense of my colleagues that we did use them as guinea pigs, and we were trying this out, and they may not have all the relevant information at the right time and so forth. So I'll give them that. But then, and I think I'll end with this because I am truly running out of time. We did the same thing. We did the same thing with MBA students, and they turn out to be a lot more rational. I want to say they did impose a tax that hovered around 1 because they didn't want to damage their own economies too much. But they also realized they had to contribute a little bit. And you see the team that represented Russia didn't want to impose too much tax, but because in fact, they are on the left side of the optimal temperature. And so from their own economy's point of view, warming would be a benefit from them, right? But they still contributed a little bit. And so here's the corresponding emission curve that is close to standard tax. And so they didn't quite manage to limit warming to 1.5 degrees, but they also didn't fry the planet, as we saw in the previous example. So that was a very interesting experience. And we also, I don't have time to go into this, but we also had surveys before and after, and we saw a change in attitude from the MBA students, where before there was a small group that thought there was a very small chance that we would limit warming to 1.5 degrees. That's the blue part of this cake, and that blue part of the cake grew. So they realized, oh, limiting warming to 1.5 degrees is going to be really hard. And maybe that's a good point to end on because I've run out of time. So thank you all.
Thank you very much, Trude. Very interesting. I think I myself has numerous questions, but we can take a couple of questions in the audience. One question from me while you were thinking was the fact that you have this 1 year step compared to half an hour, or what you said?
Half hour, yeah.
Half hour. Have you considered changing the 1 year step to half a year, or making it more similar to the climate model?
I don't think that's one of the first things that we would move to. I think a lot of the measures of economic activity and tend to come in annual numbers. And it's a thought, but I think it's unthinkable that the economic model would come to a half-hour time step anyway. So they would never really converge, I think, anyway. So I think maybe a more logical way forward is to find a good way to handle the scale mismatch, yeah.
But handling the scale, you need to do that because these extreme events, they come stochastically more than on 1 year basis, so they will happen in a 2 month span, in 2 days, and then disappear again. How
Indeed.
Can these be handled?
Yeah, you would have to keep some count on the frequency of occurrence of extreme events per year from the climate model would be one way. So, but there are a number of challenges that come with the fact that there are such different scales that we're dealing with. Yeah. So this is one of them.
One more question from me was about this example here. We should have heard more about that. What are the next steps for these types of scenarios for students? Because this is something that is kind of interesting, that might help us to understand how to get forward towards the 1.5 degree or at least 2 degrees.
Indeed. I'm thinking maybe the best way to have impact is by getting MBA students to understand that doing this is going to be hard. No, but what we're doing now, we plan to build on. So we plan to continue to use it in courses. We have to take the modeling framework that we have now and turn it into, we probably will have to build an emulator of the modeling tool because it's too expensive to do teaching at a large scale. the way it is now. It takes about a week to run 100 years, so it becomes too slow of a process. And we have an industrial collaborator. They create online educational games, and so they are very keen to take this to their platform so that it can be available in all regions of the world. And so this is definitely something that we're planning to build on, but we've had to go through these rounds of testing it out on whether it's our colleagues or MBA students or whatever. Yeah.
Okay, thank you. I take 2 questions. First down there, and there's another one. These 2 questions is okay. Yeah, please state your name and question.
Yeah, I'm Toyan Wei from CICERO. That's very interesting talk. In fact, CICERO, we have tried to do something similar, but at the country level or regional level, rather than this very gridded level. Yeah. So but I have one mainly can be comments. Yeah, maybe quite many comments, I think. Yeah, on the damage function. Yeah. In fact, there are a lot of studies on damage functions. At the sectoral level rather than GDP as the aggregate indicator. At the sectoral level, they also consider not only temperature change, they also consider precipitation and also other things. Sea level rise, and the heat waves and extremes. There's a lot of studies on this at the sectoral level. And especially for this damage function, if you only consider the GDP losses, that's not really aggregate effect. Because if you have the same GDP level, but if a country is dominated by agriculture, it will be heavily affected by the temperature change. But if it's dominated by services, then nothing, perhaps. Yeah.
I'll try to answer quickly. So this study here is done on the sector and regional level, and then is aggregated up. So the results that kind of lie behind this are specific to countries. So it's not the same function everywhere, but it's country specific, and so reflects the sectors. Yeah, sector. Yeah, so that's underlying here, and so you're right. So for example, countries that rely heavily on agriculture would be most likely more sensitive, right? So I think, yeah, there are lots of really interesting work going on when it comes to damage function. And so the challenge then is just to build a modeling framework that can incorporate the damage function studies with greater detail, whether it's, regional specific damage functions or sector specific damage functions. But I think that's probably the way to go forward, because when you aggregate up, you're right, you lump things together and probably inflate uncertainty in that way. Yeah.
One more question down there, and then we'll close the session.
Thanks for the talk. I had a question about the spatial and the time resolution of the NORIASM simulation. I was wondering, since you said that it's computationally heavy, I was wondering, can't we take adaptive resolution over different regions of for example, I don't know, central part of Australia should be static over the course of, 3 months. Like we have high resolution for some regions and low resolution for some other regions. Yeah, that was my question. Yeah.
Absolutely, yeah, and that's a kind of a frontier of climate modeling or Earth system modeling, is that we have these adaptive grid where, depending on the question you're asking, you can run at much higher resolution in certain regions. And for this application, maybe we would go to regions that have more extreme events and can zoom in there. For more like climate science questions, you would maybe zoom in on regions where you have strong amplifying climate feedbacks, for example, potentially. And so that's an excellent suggestion, and is sort of at the frontier of Earth system modeling at the moment.
Okay. Thank you very much, Trude. Very interesting. I think you have to come back very soon to talk more about this. And there will be more dScience events here at the Science Library, and also at where we have our launch. And of course, do remember Data Science Day on the 17th of October. A lot of interesting are going to happen. Thank you very much.
Thanks for coming.